like to have the whiteboard kind of approach like we have in the class. So I'll give it a try. I have paper in front of me. I'll focus my camera onto the paper, and then I'll continue speaking and explain things on the paper. I hope that should be okay. All right, it's fine. Ramanand?
There is a lot of lag.
Can you see the video?
Yes, sir, I can see the video.
Okay. To begin with, first we'll try to understand what basically is a deal. To understand, when data has to be sent from one PC to another PC, it goes in the form of packets, that is small packets that are sent. For example, I have here PC, transmit it as small packets. Now, with respect to this, when a packet is sent by the computer, which we would say is a sender, there would be some time for this packet to reach to the destination. I would say here, destination. This lapse of time, this time that it takes to move from the sender to destination involves certain types of delays. We don't expect it to leave here and reach here at the same time, something that you might have seen in Shaktiman. Here you would have some delays. Just a moment. Just sip. We would expect some sort of delay while the packet leaves from the sender to the host. This is what we know as delays in packet switching. There are 4 types of delays that we come across when a packet is moving from the sender to the destination. The 4 delays that we come across are the transmission delay, the propagation delay, the queuing delay, and processing delay. Yeah, Mary, no, it's not clear. My voice is not clear? Or video is not clear?
Voice is not clear.
I'll try to speak louder. Is that? Okay, video is not clear. So, do I need to zoom it in or some other issue? Is it lagging? All right, let's give it another try. I'll be a bit, I'll write a bit big. Now let's start with the first delay that we come across. First thing that we understood is our today's topic would be delays. That is, when a packet travels from one node, that is the sender, to the destination, it would have certain delays. It would suffer from several type of delays. And the prominent or important delays that come across are 4: nodal processing delay, queuing delay, transmission delay, and propagation delay. And together all of these we call them as total nodal delay. Now, if you see the slide, go on to slide number 44. It shows that packets queue in a router buffer. To understand this, I will first draw a figure here in which we have a sender here, that is A, a sender here, that is okay. Now both are connected to a routing device here. I will call this routing device as router. What is it? We are going to discuss in coming classes. And then I have a destination here that I would call as D at the router. Now, I expect packets to be flowing from A as well as from B, and then the router would send it to D. Let's say we have another link here goes to the first delay that we come across would be processing. Now, what is processing? You see, the packet started arriving at router R from A as well as B. A's packets is denoted by red and B's by green. Red ones are supposed to go to, let's say, C. So destination of this is this one. And the destination of green packets is this. So when the packet arrives at the router R, the first thing that it faces is known as processing. So I would take this processing delay here. At the entry of the router, I have the first delay, which I will call as processing. Now, what is this processing? When A has sent this packet, packet number 1, within this packet number 1, there is a place which mentions that my destination address is this, the destination IP address. My source address is this, that is from A. Let's say my source is A and destination is C in this case, which would be in this case, these IP addresses. When it reaches the router here, the router would take some time to open this packet and look at the destination address of the packet. So this time that it takes to look at the destination, why does it need to look at the destination? Because it has to figure out that from this incoming link, where should I pass this packet to? Should I push this packet onto this link or should I push the packet to this link? How would it decide? It would have its own mechanism. We are going to study that in future. As of now, keep in mind that some time would be taken by the router to check the packet's destination address and then decide that this packet should be pushed from here onto this link. Number 1. Certain other things that are done by the router would include checking whether this packet has some error or not. Typically, errors occur in wireless or wired ring. So these things would take some time. This time that is taken by the router is known as processing. And how much do we expect this? Nowadays, we have very high-speed routers, so we expect these processing delays to be of the order of microseconds or lesser than the microseconds. So this is the first part that we have as processing delay. Any question? Okay, video is not visible. Raman, what do you say?
Sir, video is not at all clear to everyone.
Then what do you suggest?
Sir, like yesterday, what we have done.
All right. Yeah, but I wanted this figure to be displayed. Wanted something. Is there a whiteboard within it? Okay, let me redo the meeting then. Let's see what sheet. If any issue, just tell me. Okay, so we were discussing the first delay, that was the processing delay. Any question about processing delay? No. Okay. Now, as per the figure that I had drawn just now, this was our router. This is the figure that we give with respect to router across, I'll say R. These were the incoming links. One was from A, another one was from B. There were two destinations here. One was D and another one was C. So we went across and we saw the first delay, that was the processing delay. The second delay that we have is known as a queuing delay. Let's understand what a queuing delay is. Now, once you go to your hostel mess, there are two chances. If you go early, there's nobody in the mess, you go and take your food. Ramanan?
Hello, sir.
Yeah, there's some people who I need to, press admit every time. So that might disturb our whiteboard. We need to figure out why they need to be, added. Can't they directly join like others have joined?
Sir, you come out and guide me.
Okay. Now, so I was explaining a situation in the case that you are going to the mess and there is nobody there. You go, you were the first one to arrive, you go and you take it. And another situation in which you reached a little late, there are some people which are already there. If there are some people already waiting for food, what would you do? You would go and add yourself in the line for food. That is what we have a queue here. And exactly the similar way, what we have here is, this is our router. When A and B started to send packets, this is D, this is C. Some packets were already from A to C. In that case, what happens to the packet who are being sent from B? That are these. Since router R is busy with transmission of packets from A to C, the packet coming from B would need to wait for its chance. How they would be taken? There are different, routing principles, algorithms, which would take care of it, which we'll see later on. But as of now, there would be some time which packets coming from B would have to take. This is what a packet experience as a queuing delay. Means a delay in which a packet would have to wait to be transmitted onto the outgoing link of the router. Now, how much would this delay be? The question can arise here. Depends. I cannot say that it's this much because router's capacity is this much, so delay is this much. No. It would depend upon how many packets have earlier arrived, number one. The router is busy with those packets. And how many packets are already in the queue? Like I said, you came early to the mess, you got earlier served. You come late, you might have to wait for a queue. It's like that. If queue is empty, no other packets within the queue, our queuing delay would be equal to 0. On the other hand, if we see that router is already busy serving the packets that are coming from A, in this case, we would have a longer queuing delay. Generally, the queuing delays are of the order of microseconds to milliseconds. This is the second delay that we face. Is this fine? All right. I move on to the third delay. If you go to the slides, I am talking this time about, transmission delay, and transmission delay can be found in slide number 46. Let's see what a transmission delay is. Now, please, let's say assume that we have first come, first serve, right? Now, some packets are being transmitted before you or before this packet, and now this packet would get a chance to be transmitted. So, as per the figure, I had, let me change the color. I have now a packet which has been reached here. How? After the first delay I will depict with this. This is the first delay, that was the processing delay. After processing delay, it took the second delay, that was the queuing delay. And after queuing delay, now it is the chance for this packet, which is denoted by pink here, to be transmitted. That is this one. It would take some time for this packet to be pushed onto the outward link, that is here. So the time that actually this packet takes to be pushed onto the transmission link is known as the transmission delay. It is not the time that it takes on the link to move from the router R to C. No. It is the time that router takes to move this packet from inside to the link through an interface here. What is an interface? You understand interface, network interface card and so on, that we'll be discussing in the layer 1, that is the physical layer. Why it takes time? Well, you understand that there would be a packet which is already transmitting from the router to C. So it waits for that to finish. And then when the packet is to be transmitted, the packet is a long packet. What is basically a packet? It is zeros and ones. Zeros and ones, what we say? stream of zeros and ones, something like this. So this stream of zeros and ones would require some time to be pushed from the first bit in the front to the last bit at the end. How would we explain it here? We would explain it in the sense that, let's say L bits is the length of packet, and the transmission rate from router here to C is R, and transmission delay, I will denote by ED. It is equal to the length that we have divided by the rate at which it is transmitting, that is L by R. Or in other words, we say, for an example, if we have a 10 megabit between router R and C, or the transmission rate of is 10 Mbps, the length of a packet to determine, depending upon how much the length of packet it is, you can try to find L by R, that would be the transmission delay. Okay, any questions here? Right. So what we saw, first one, nodal processing, that is the time taken by the router, that is the first black line that is denoted here. Then the time taken by the router and the last delay that we come across here is propagation delay. As the name itself would say, propagate. Now our packet has reached to this link. I would use another color. Now it is here. What is this green denoting? This is denoting the start of the link here from the interface of the router up to the time that the packet has reached this C. So once the packet has been pushed from the pink, that would be the transmission delay, onto the interface or the start of the link, the packet needs some time to move from the router's interface and reach the node that is C, from R to C. So it would involve the time that the packet takes while moving over the link, the actual link. So we have moved beyond the router. We are talking about the time that is required to propagate from the beginning of the link to the router, from the router R to the node C. This is denoted by propagation delay. How much would be the propagation delay? How much would be the time that the bit takes? The bit takes the time of propagation as per the speed of the link. Now, how much is the speed of link? It depends upon what you are using to transfer the data. If you're obviously transferring over a fiber link, it would be very fast. Why? Fiber has the capacity of transmitting at the rate of gigabits. Compare it with a twisted pair of a copper wire. It can range from 2 into 10 to the power of 8 meter per second to 3 into 10 to the power of 8 meter per second. I mean 3 into 10 which would be basically the speed of light, which can be the speed of transmission in fiber optics. These transmission media will be taken care when we start with the layer 1 of OSI, that is the physical. If you have any questions till now, you can just unmute your microphone and ask the question. Anybody? All right. If I now compare if there is something in the chat, no? Okay, then I will return to the whiteboard and go to slide number 47. It's a good example to understand what we have just now discussed. The segment from A to C, this can be considered as a road, okay, a highway, and the router that we have are in between. Consider that as a toll booth. It's the booth where you pay in the tax to use the road. Now, car here is a bit, and we are taking 10 cars forming a packet. So a packet of 10 bits each. It propagates on the highway at the rate of 100 kilometer per hour. So from the time A to R, the picture is given there, you can check the picture. Now we would have the next 10 cars, again a packet, traveling together as one caravan would be 10 cars. Take caravan as a packet, a car as bit. Now, the question here would be, try to understand each delays with respect to this example. It also says that each toll booth would take around 12 seconds for one car to transmit. Okay. And when the first car of the caravan arrives at a toll booth, it waits at the entrance until the 9 other cars have arrived and lined up behind it. Which means that the entire caravan must be stored at the toll booth before it can begin to forward. See now how these times are analogous. Now, first it has to wait for the entire caravan of cars to come. The time that it would require for the toll booth to push the entire caravan onto the highway would be the transmission delay. Right? And also, how much time the car would take from the exit of the first toll booth until it reaches the next toll booth would be analogous to propagation delay. Why? Propagation delay depend upon the thing. Okay. Because propagation delay would depend upon how far is one toll booth from another toll booth. That would be the propagation delay. Now there would be, let me see this slide. A question, how long until the caravan is lined up before second toll booth? Have a look at it. Okay. If you have any questions, we can discuss that in this class. Also, there is a question, will cars arrive to second booth before all cars are serviced at the first booth? Look at that as well. Okay. Now moving on to the second part of it, which is packet loss. So we have this topic as internet delays and packet loss. What is this packet loss? Let's go back to the whiteboard. I have a node here that is A. I have another node here which is B. Try to understand this. I'll try to be slow in making you understand what packet loss here is. This is our router. I denote this by R. These are my links connecting this to destination, and the destination is C. Each link would have its carrying capacity, how much data it can transmit over a specific period of time. The link here between A and R, let's say it has the carrying capacity of 5 Mbps. And the link between B and R would have a carrying capacity of, again, 5 Mbps. And the link between R and C is 8 Mbps. Now what can happen here is A starts transmission of packets. Fine, as long as A is transmitting at the rate of 5 and the transmission capacity of R and C is 8, there is no issue. But what if B also starts transmitting at the same time at the rate of 5 Mbps? We would have router to transmit both packets of A as well as B. But A and B are transmitting at the speed of 5 plus 5, that is 10 Mbps. And the link between the router R and C has the capacity to carry only 8 Mbps. In this case, what happens? A router has a certain carrying capacity known as a buffer. So it would have a memory wherein these packets be stored temporarily, a temporary buffer. It's simply a waiting place, a memory wherein you will keep these packets. But keeping in mind that it's a memory, it's not an infinite memory. It has a finite capacity. And if the router is overwhelmed by A and B by sending many packets, this capacity goes up to the full. And what happens after that? After that, once it's full, the packets are dropped. So we'll have some packets to be dropped from red one and some packets from blue ones. This is what we call as packet drop. You can call it as a packet loss. which also means that a packet which is sent by A does not reach to the destination because of a certain error or because of the carrying capacity of the link. An error would occur which we know as packet loss. Now, due to this transmission of 5 and 5 Mbps, we had a queue filled. Just now we understood what was the time that a packet took within the queue. It was the queuing delay. Now, another point that we come across here, which we would see, let's say it's mentioned in some slide. I'll go back to slide number 46. Can you go back to slide number 46? Yeah. If you see there, it mentions now how much would be the total delay that a packet has suffered. The total delay is known as the nodal or total nodal delay, which is equal to the processing delay, I will write as PRD, plus the delay at the queue, so I will write it here as QD, plus the transmission delay, which I would write here as TD, plus the propagation delay. This would give us an end-to-end delay if we add all the total nodal delays that occur for each of the packets while transmitting from one node to the other. So we are done with the delays. We're done with the packet loss. We move on to slide number 53, which is throughput. Now, what is basically throughput? You have heard about, data rate, terms like throughput, terms like goodput. Throughput is basically if you have sent the data across a link, how many bits or how many packets did you receive over a period of time? The actual useful data that you have received over a period of time is basically throughput. What do you say? Bits per second. There are two types of throughput that we come across. One is the instantaneous throughput, another is the average throughput. Instantaneous is like just now you check your speed of internet and you say, okay, this time I'm getting 1 Mbps. And average would be over the period of last one day, what was your internet speed? So they would average all the instantaneous throughputs and give you the average of these. Another term that is related to the throughput is known as goodput. Goodput is actually throughput but taken at an application layer. This we will again discuss when we reach the application layer. This should be the end of our topic for today, right? I'll take tomorrow the lab in which we'll try to understand these terms like delays, the throughput and so on. Mostly we'd use the tools which are existing like the ping tool and so on. Other tools that are mentioned in the PPT that I have shared in the Google Classroom can be downloaded. Better download earlier so that You can try it at the same time. So I'll be there tomorrow to guide you through the lab, the first lab that you will have. Any questions? Yes, Ramanand. So
Yes, sir.
how are we supposed to submit lab assignment, handwritten or doc file? It would be a doc file because you need to take screenshots of the lab. Let us go through it tomorrow. Okay. If we start today, it will take around 1 hour more. So let's better take it tomorrow.
Okay.
Okay. Then I'll inform you how you're supposed to submit your lab assignment. And regarding your reading assignment, I mean, I don't expect it to be submitted as of now, but please go through those topologies that I mentioned yesterday, the star, the bus, and so on. If time permits, we can discuss them as well. Please go through the LAN, BAN, MAN, WAN, SAN, right? All these terms that you come across, I can put on the list of these terms. I'm talking about storage area network, wide area network. I'll put those in Google Classroom as well. Okay, that would be for reading. All right, anything else?
So tomorrow at 12.
If 11 is convenient to you, 11 is fine with me.
Okay.
All right, okay. See you then.